All right, let's jump straight into this explainer and unpack the absolute magic behind how machines literally learn to see. If you've ever found yourself wondering how on earth an AI can instantly spot a face, a stop sign, or a dog in a crowded photo, you are in the exact right place. Today, we're zooming in on topic 6.2, deep learning, and specifically section 6.2.1, the convolutional neural network. Here's our game plan for today. We're going to cover the shift to deep learning, tackle this massive issue called the parameter explosion, introduce the CNN, walk through a really helpful microscope analogy, and wrap up with how layers and volumes create deep complexity. Let's get to it.
Section 1. The deep learning shift. Let's ground ourselves in what this term actually means before we tackle the visual side of things.
Okay, so the phrase deep learning gets thrown around constantly, right? But the actual technical definition is surprisingly straightforward. It's not magic. It's literally just a neural network that has grown to have more than 2 hidden layers. For a long time, the machine learning community really struggled to train networks this deep. So today, the term practically refers to utilizing modern mathematical toolkits to solve complex problems, regardless of the exact layer count.
You see, for decades, training these really deep networks was basically blocked by a massive headache known as the vanishing gradient problem. Think of it kind of like a giant game of telephone across a network. Traditional activation functions caused the learning signal to just drop off exponentially as it passed backward through the layers. The early layers will literally just stop learning, but modern tools, specifically the ReLU activation function, absolutely blew the doors wide open on this. It suffers way less from that vanishing gradient, which means computer scientists can finally scale these networks up to hundreds or honestly even thousands of layers.
Section 2. Parameter explosion. So what happens when we try to force a high-dimensional image into one of these standard neural networks? Well, we hit a brick wall. If you try using a standard multi-layer perceptron network for an image, it triggers this completely intractable explosion of parameters. Look at it this way. Just adding a single 1,000-unit layer to a standard network adds over 1 million new parameters to your model. Now, imagine feeding in a crisp, high-resolution smartphone photo. You're suddenly dealing with billions of parameters. It would instantly crash your average computer. The input is just so high-dimensional that optimizing the model becomes mathematically impossible. Section 3. Enter the CNN. To fix this massive system-crashing data problem, researchers came up with a brilliantly efficient workaround.
They needed a way to handle intense visual data without that explosive parameter growth. And that brings us to the hero of our story, the Convolutional Neural Network, or CNN. By drastically slashing the number of parameters, CNNs have become the absolute gold standard for processing things like images and text. Fun fact, early versions of these were actually used back in the 90s just to read handwritten zip codes on mail. They are perfectly designed to cut the computational bloat while keeping incredible accuracy. But to really grasp why they work, we have to look at how images themselves are actually built.
There's this foundational, almost philosophical insight about how images function at a pixel level. Think about a photo of a face against a bright blue sky. Massive patches of those pixels are basically identical, right? Just pure blue sky or continuous skin tone. The real juicy information, the exception to the rule, is found entirely at the edges, exactly where two different objects meet.
Section 4. The microscope analogy. So, if nearby pixels are mostly identical, we just need a smart way to detect those edges where things change.
If a neural network can spot both the uniform regions and the edges, it can accurately predict the object. Which leads to the million-dollar question. How do we efficiently hunt for these edges without feeding the entire massive image in all at once and, again, crashing our system?
The secret is a moving window. Imagine you are looking at a dollar bill under a microscope. You can't see the whole bill at once, right? You have to slowly move your view from left to right and top to bottom, scanning it piece by tiny piece. This is exactly how a CNN processes an image. It splits it into smaller, completely manageable square patches. And at every single tiny stop of that microscope, the network performs a specific math operation called a convolution. Essentially, a tiny regression model inside the network learns to spot a very specific kind of pattern within that little patch of pixels.
Let's break down the actual anatomy of this algorithm step by step. First, it isolates a patch, let's say a 3x3 pixel grid. Next, it calculates a dot product between that specific image patch and a pre-learned filter matrix. Then, it simply sums those resulting values together.
And finally, it tacks on a bias parameter.
Picture this building visually. The filter convolves, or essentially slides, across the input image from left to right and top to bottom. At every single iteration, it is multiplying the pixels in the patch by the numbers in the filter and adding them all up.
In the source text example, they look at a patch shaped like a cross. When we mathematically match that cross-like patch against a cross-like filter using our dot product, we get a sum of 12.
But what does a 12 actually mean to the machine? Well, the absolutely crucial takeaway here is that a high number means the network successfully found the specific shape or edge it was looking for in that tiny patch. If we ran that exact same cross filter over a patch shaped like a T, the math would output a much lower number, like 9. The more the patch looks like the filter, the higher the convolution value. This is literally the machine learning to see a specific edge, very much like your own brain does when you look at a silhouette.
Section 5. Deep complexity. But how do we scale this up from a flat, black and white 2D shape to the rich, incredibly complex images we actually see in the real world?
Well, real life has color because color images have red, green, and blue channels. Our simple 2D grid transforms into a 3D volume, and the math elegantly expands to handle this. The network simply sums the convolutions across all 3 color matrices at the exact same time. So that sliding filter isn't just a flat square anymore. It's practically looking through the depth of all the color channels simultaneously.
And keep in mind, a CNN doesn't just use one filter. By stacking multiple filters in a single layer, the network can scan for horizontal edges, vertical edges, and complex textures all at the exact same time. Every filter creates its own output matrix, and this is where it gets truly deep. The next layer in the network treats the massive stack of outputs from the previous layer as its brand new input volume. Oh, and tying it all back to the start of our explainer, that ReLU activation function is applied right after the bias term is added, which is what allows these networks to remain computationally stable no matter how deep and complex they get.
It really leaves you in awe of the sheer scale of modern AI. Think about it. Millions of filters, operating across thousands of layers, instantly recognizing not just a simple edge, but a specific human face in a totally crowded room. If basic matrix math can allow a machine to see our world this clearly today, what on earth will these networks be capable of seeing tomorrow? Thanks for joining me on this explainer, and as always, keep your curiosity sharp.